A supernova is the explosive death of a star. But not just any death. This isn't a star quietly fading away like a candle running out of wax. This is a star detonating with such ferocity that it outshines entire galaxies. For a brief, brilliant moment, a single dying star can emit more light than the combined glow of hundreds of billions of other stars. The word itself comes from the Latin nova, meaning new, because when ancient astronomers saw these sudden bright spots appear in the night sky, they thought they were witnessing the birth of new stars. They weren't. They were watching stars die. But what a way to go. The super prefix was added in the 1930s by astronomers Walter Baade and Fritz Zwicky, who realized that some of these stellar explosions were far more powerful than ordinary novae. They coined the term supernova to distinguish these cosmic titans from their smaller cousins. Zwicky, in particular, was obsessed with these events, and he was right to be. He understood that supernovae weren't just astronomical curiosities. They were universe-shaping phenomena. To put the energy scale in perspective, consider this. A typical supernova releases approximately 10 to the power of 44 joules of energy. Written out, that's a 1 followed by 44 zeros. The human mind cannot truly comprehend that number. For comparison, the largest nuclear bomb ever detonated, the Soviet Tsar bomber in 1961, released about 2.1 times 10 to the power of 17 joules. A supernova releases roughly 100 billion times more energy than that bomb, in a matter of seconds. And here's what's truly mind-bending. Most of that energy doesn't even come out as light. About 99% of the energy released in a core-collapse supernova escapes as neutrinos, ghostly particles that barely interact with matter. The remaining 1%, the part we can actually see, is still enough to outshine everything else in the host galaxy combined. Supernova aren't just spectacular light shows, they're cosmic factories. They forge the heavy elements that make up planets, moons, and even you. The calcium in your bones, the iron in your blood, the gold in your jewelry, all of it was created in the heart of dying stars and scattered across the universe by supernova explosions. You are, quite literally, made of stardust. And that stardust was delivered by violence on an unimaginable scale. To understand how a star dies, you first need to understand how it lives. And the life of a star is defined by one eternal struggle: gravity versus pressure. Stars are born in vast clouds of gas and dust called nebulae. Over millions of years, gravity pulls this material together, compressing it tighter and tighter. As the material collapses, it heats up. Eventually, the core becomes so hot and dense that hydrogen atoms begin to fuse together, forming helium and releasing enormous amounts of energy in the process. This is nuclear fusion, and it's what makes a star shine. The energy released by fusion creates an outward pressure that pushes against gravity's inward pull. For most of a star's life, these two forces are in perfect balance. This equilibrium is called hydrostatic equilibrium, and it's what keeps stars stable for millions or billions of years. Our Sun has maintained this balance for about 4.6 billion years, and will continue to do so for another 5 billion or so. But here's the catch. Fusion requires fuel, and eventually every star runs out. What happens next depends entirely on the star's mass. Small stars like our Sun live relatively quiet lives and die relatively peaceful deaths. When the Sun exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, shed its outer layers as a beautiful planetary nebula, and leave behind a dense core called a white dwarf. No explosion, no supernova. Just a slow, graceful fade into cosmic retirement. But massive stars, those with at least 8 times the mass of our Sun, face a very different fate. These stellar giants burn through their fuel much faster. While our Sun will shine for about 10 billion years, a star 20 times the Sun's mass might exhaust its fuel in just 10 million years. That sounds like a long time, but in cosmic terms, it's the blink of an eye. These massive stars don't just burn hydrogen. Once the hydrogen is gone, they start fusing helium into carbon and oxygen, then carbon into neon and magnesium. Then neon into oxygen and magnesium, then oxygen into silicon and sulfur, and finally silicon into iron. Each stage of fusion releases less energy than the one before and lasts for a shorter time. The hydrogen burning phase might last millions of years. The helium burning phase, maybe 1,000,000 years. Carbon burning, perhaps 1,000 years. Neon burning, a few years. Oxygen burning, a few months. And silicon burning, the final stage, lasts only about a day. By the end, the star's core resembles an onion, with layers of different elements surrounding an iron core at the center. And iron, beautiful iron, is where everything falls apart. Iron is special in physics. It sits at the peak of what's called the binding energy curve. Elements lighter than iron release energy when they fuse together. Elements heavier than iron release energy when they split apart, which is how nuclear fission works. But iron itself, iron does neither. Fusing iron or splitting iron requires energy input. It doesn't give energy back. This is why iron is called the ash of nuclear fusion. It's the end of the line. Once a massive star builds up an iron core, it has nothing left to burn. No more tricks, no more fuel. The fusion furnace that has kept the star alive for millions of years suddenly goes cold. And when fusion stops, gravity wins. The iron core, now with a mass of roughly 1.4 solar masses and a diameter about the size of Earth, is supported only by electron degeneracy pressure. This is a quantum mechanical effect, where electrons resist being squeezed together. But there's a limit to how much pressure electrons can provide, known as the Chandrasekhar limit, named after the brilliant Indian-American astrophysicist Subramanian Chandrasekhar. When the iron core exceeds this limit, approximately 1.4 times the mass of our Sun, electron degeneracy pressure fails. The core can no longer support itself against gravity. What happens next occurs in less than a second, and is one of the most dramatic events in the universe. The core collapses, not slowly, not gradually. It implodes at about 1/4 of the speed of light. That's roughly 70,000 kilometers per second. An object the size of Earth compresses down to something about 20 kilometers across in a fraction of a second. The density becomes so extreme that protons and electrons are forced to merge, forming neutrons and releasing a flood of neutrinos. The collapsing core releases gravitational potential energy on an almost incomprehensible scale. About 10 to the power of 46 joules of energy is released, with 99% carried away by those neutrinos. The neutrino burst from a supernova is so intense that if you were somehow within a few parsecs of the explosion, the neutrinos alone could kill you, despite the fact that trillions of them pass through your body every second without you noticing. The collapse continues until the core reaches nuclear density, about 10 to the power of 17 kilograms per cubic meter. At this point, the neutrons themselves resist further compression through neutron degeneracy, pressure, and the strong nuclear force. The core suddenly stiffens and rebounds like a compressed spring. Meanwhile, the outer layers of the star are still falling inward, unaware that the core has stopped collapsing. They crash into the rebounding core at tens of thousands of kilometers per second. The collision creates a powerful shockwave that propagates outward through the star. For a moment, the shockwave stalls. The infalling material is too much, but the flood of neutrinos from the core deposits just enough energy into the region behind the shock to revive it. Within hours, the shock wave tears through the star's outer layers, accelerating them to speeds of 10,000 to 30,000 kilometers per second. The star explodes. A supernova is born. Not all supernovae are created equal. Astronomers have identified several distinct types, each with its own mechanism, characteristics, and cosmic significance. The classification system can be confusing because it is based partly on what we observe in the explosion S-light spectrum, and partly on the physical mechanism that causes the explosion. The first major division is between Type 1 and Type 2 supernova. Type I supernova lack hydrogen lines in their spectra. Type 2 supernova show strong hydrogen lines. This might seem like a minor detail, but it tells us something profound about the star that exploded and how it died. Type Ia supernova are special. They don't come from massive stars at all. Instead, they involve white dwarfs, the dense remnants of sun-like stars that have already completed their life cycles. A white dwarf is an incredibly dense object, packing roughly the mass of our sun into a volume about the size of Earth. A teaspoon of white dwarf material would weigh several tons. These objects are supported against gravity by electron degeneracy pressure, the same quantum mechanical effect we discussed earlier. Now, imagine a white dwarf in a binary system orbiting close to another star. As the companion star evolves and expands, material can flow from it onto the white dwarf. The white dwarf grows more massive over time, slowly accumulating matter on its surface. As the white dwarf approaches the Chandrasekhar limit of about 1.4 solar masses, the pressure and temperature in its core increase dramatically. Carbon and oxygen, the primary components of the white dwarf, begin to fuse. But unlike the controlled fusion in a normal star, this happens all at once, throughout the entire white dwarf. The result is a thermonuclear explosion that completely destroys the white dwarf. Nothing is left behind. No neutron star, no black hole. Type Ia supernova are remarkably consistent, because they all involve white dwarfs exploding at essentially the same mass. They all produce roughly the same amount of light. This makes them excellent standard candles for measuring cosmic distances. By comparing how bright a type Ia supernova appears to how bright it actually is, astronomers can calculate how far away it is. In 1998, two independent teams used type Iai supernova to make one of the most shocking discoveries in the history of cosmology. They found that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, all thanks to exploding white dwarfs. Type II supernova are what most people think of when they imagine a supernova. These are the classic core collapse explosions we described earlier, where a massive star exhausts its fuel, builds up an iron core, and implodes. The hydrogen lines in their spectra come from the massive star's outer envelope, which still contains plenty of unfused hydrogen when the core collapses. As the shockwave blasts through this envelope, it heats and ionizes the hydrogen, producing the characteristic spectral lines. Type II supernova show considerable variation. Type IIp, the most common type, shows a plateau in their light curve, where the brightness stays roughly constant for several weeks. This plateau is caused by the recombination of ionized hydrogen in the expanding envelope. Type IIL shows a linear decline in brightness without a plateau, indicating the star had a smaller hydrogen envelope when it exploded. The progenitor stars for Type II supernova are red supergiants, massive stars that have swelled to enormous sizes as they approach the end of their lives. Betelgeuse, the bright red star marking Orion's shoulder, is a red supergiant that will likely explode as a Type II supernova sometime in the next 100,000 years or so. When it does, it will be visible in broad daylight and might even cast shadows at night. Type Ib and Type Ic supernova are also core collapse explosions, but with a twist. These stars have lost their outer hydrogen envelopes before exploding. Type Ib shows helium lines but no hydrogen. Type Ic shows neither hydrogen nor helium. How does a star lose its outer layers? There are two main possibilities. The star might have been in a binary system, with a companion star gravitationally stripping away its outer layers over time. Alternatively, the star might have been a Wolf-Rayet star, an extremely massive and luminous star, whose powerful stellar winds blow away its own outer atmosphere. Type Ic supernova are particularly interesting because some of them are associated with gamma-ray bursts, the most energetic explosions in the universe. These long-duration gamma-ray bursts are thought to occur when the core of a rapidly rotating massive star collapses directly into a black hole, producing jets of material that blasts through the star's poles at nearly the speed of light. When the explosion fades and the debris expands into space, something remains at the center. What that something is depends on how massive the original star was. 4 stars between about 8 and 25 times the mass of the Sun. The collapsed core becomes a neutron star. This is one of the most extreme objects in the universe. A neutron star packs roughly 1.4 to 2 solar masses into a sphere, only about 20 kilometers in diameter. The density is almost incomprehensible. A sugar cube of neutron star material would weigh about 1 billion tons, roughly the mass of Mount Everest. Neutron stars are supported against further collapse by neutron degeneracy, pressure, and the strong nuclear force. Their surfaces are composed of a crystalline lattice of iron nuclei, with a thin atmosphere of hydrogen and helium. Beneath the surface, matter becomes increasingly neutron-rich, until the interior is a superfluid sea of neutrons with exotic properties that physicists are still working to understand. Because angular momentum is conserved during the collapse, neutron stars spin incredibly fast. A star that rotated once every few weeks becomes a neutron star spinning multiple times per second. The fastest known pulsar pairs RJ-1 Pat 11246A D spins 716 times per second. The surface at its equator is moving at about a quarter of the speed of light. Neutron stars also have incredibly powerful magnetic fields, trillions of times stronger than Earth's magnetic field. These fields channel radiation into beams that sweep across space as the star rotates. If one of these beams happens to point toward Earth, we see regular pulses of radiation, which is why rapidly rotating neutron stars are called pulsars. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The signals were so regular that the researchers initially nicknamed the source LGM-1. 4 little green men, half-jokingly wondering if they had detected an alien signal. They hadn't, but what they found was arguably more exciting. A new class of extreme stellar remnants that has since taught us enormous amounts about physics under conditions impossible to replicate on Earth. 4 stars, more massive than about 25 times the mass of the Sun. Even neutron degeneracy pressure cannot halt the collapse. The core keeps falling inward, compressing past the point of no return. A black hole forms. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. The event horizon isn't a physical surface. It's a boundary in space-time, the point beyond which the escape velocity exceeds the speed of light. Cross it, and you're gone. No coming back. No messages. Nothing. At the center of a black hole, according to general relativity, lies a singularity, a point of infinite density where the known laws of physics break down completely. Most physicists believe that a complete theory of quantum gravity will eventually reveal what actually happens at the center of a black hole. But we don't have that theory yet. Black holes are places where our understanding of the universe reaches its limits. Stellar mass black holes, those formed by supernova explosions, typically have masses between about 3 and 20 solar masses. But black holes can grow much larger by consuming surrounding material or merging with other black holes. Supermassive black holes, millions to billions of times the mass of the Sun, lurk at the centers of most galaxies, including our own Milky Way. In 2015, the LIGO observatory detected gravitational waves for the first time. Ripples in space-time caused by two black holes spiraling together and merging. This discovery opened an entirely new window on the universe and confirmed a key prediction of Einstein's general relativity, a century after it was first proposed. The black holes involved had masses of about 36 and 29 solar masses, and their merger released more energy than all the stars in the observable universe combined. All in a fraction of a second, all in the form of gravitational waves. While the core becomes a neutron star or black hole, the outer layers of the star race outward into space, forming what astronomers call a supernova remnant. These expanding shells of gas and debris can persist for thousands of years, glowing beautifully as they interact with the surrounding interstellar medium. The Crab Nebula, visible in the constellation Taurus, is perhaps the most famous supernova remnant. It's the aftermath of a supernova that was observed by Chinese astronomers in 1054 AD. The explosion was so bright that it was visible during the day for about 3 weeks and remained visible to the naked eye at night for nearly 2 years. Today, nearly 1,000 years later, the debris is still expanding at about 1,500 kilometers per second, powered partly by the rapidly spinning pulsar at its center. Other stunning supernova remnants include Cassiopeia A, the youngest known remnant in our galaxy, and the Veil Nebula, the delicate remains of a supernova that exploded about 10,000 to 20,000 years ago. These remnants aren't just beautiful. They're cosmic laboratories where we can study shock physics, particle acceleration, and the dispersal of heavy elements into interstellar space. Here's where the story becomes personal. Everything you are, everything around you, was forged in the hearts of stars and scattered by supernova explosions. The Big Bang, which occurred about 13.8 billion years ago, created only the lightest elements: hydrogen, helium, and traces of lithium. That's it. Everything else, carbon, oxygen, nitrogen, iron, gold, uranium, had to be made later through nuclear processes inside stars. During their lives, massive stars fuse lighter elements into heavier ones, building up the periodic table through successive burning stages. By the time a star is ready to explode, its core contains carbon, oxygen, neon, magnesium, silicon, sulfur, and iron, arranged in those onion-like layers we discussed earlier. But the story doesn't end there. During the supernova explosion itself, the intense heat and pressure drive additional nuclear reactions. In particular, a process called the R process, for rapid neutron capture, creates elements heavier than iron. In this process, atomic nuclei rapidly capture neutrons, one after another, building up to the heaviest elements on the periodic table before they have time to decay. The R process is responsible for creating about half of all elements heavier than iron, including gold, platinum, and uranium. For decades, astronomers believed that supernovae were the primary site of R-process nucleosynthesis. However, recent observations of neutron star mergers, particularly the event GW170817, detected in 2017, have shown that these collisions are also significant R-process factories. The debate continues about the relative contributions of supernova and neutron star mergers to the cosmic inventory of heavy elements. What's certain is that supernova explosions disperse these newly forged elements into space. The expanding remnants mix with interstellar gas clouds, enriching them with heavy elements. When new stars and planetary systems form from these enriched clouds, they incorporate those elements. That's how the Earth ended up with iron in its core, oxygen in its atmosphere, and carbon in every living thing. The astronomer Carl Sagan famously said, "We are made of star stuff." He wasn't being poetic, he was being literal. The atoms in your body, with the exception of hydrogen, were made inside stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was synthesized through nuclear fusion and released by stellar explosions. You are a walking collection of nuclear waste from dead stars, and that's beautiful. Humans have been watching supernova for millennia, even if they didn't know what they were seeing. Several historical supernova were bright enough to be visible to the naked eye and were recorded by astronomers around the world. The earliest confirmed record of a supernova comes from Chinese astronomers in 185 AD. They described a guest star that appeared in the sky and remained visible for about 8 months. The remnant of this explosion, known as RCW-86, has been identified using modern X-ray and infrared observations. Recent studies suggest it was a Type Ia supernova, occurring in a cavity blown by the progenitor system's stellar wind, which allowed the debris to expand unusually quickly. In 1006 AD, a supernova appeared in the southern constellation Lupus. That was almost certainly the brightest stellar event ever witnessed by humans. At its peak, SN 1006 was significantly brighter than Venus and possibly as bright as the quarter moon. It was visible during the day and cast shadows at night. Records of this event survive from China, Japan, Korea, the Arab world, and Europe. The Swiss monks at the Abbey of St. Golan described it as a wonderful sign that appeared in a wonderful manner. Egyptian astronomer Ali ibn Ridwan provided a particularly detailed account, noting that the star was 2.5 to 3 times the apparent size of Venus, and that its light was a little more than a quarter that of the moonlight. The remnant of SN 1006 is now one of the largest known supernova remnants, spanning about 60 light-years in diameter. On July 4, 1054, Chinese astronomers recorded the appearance of a new star in what is now the constellation Taurus. The guest star was visible in daylight for 23 days and remained visible at night for nearly 2 years. This supernova created the Crab Nebula, which has become one of the most studied objects in astronomy. The Crab Nebula is special for several reasons. It contains a pulsar at its center, the Crab pulsar, which rotates about 30 times per second and powers the nebula's ongoing emission. The nebula is a strong source of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. It's so well characterized that astronomers often use it as a calibration source, and the Crab has even become an informal unit of measurement for X-ray source intensity. Interestingly, There are no definitive European records of SN 1054, which has puzzled historians. Various explanations have been proposed, from poor weather to religious or political factors that might have discouraged recording such a strange event. Some researchers have claimed to find possible references in European sources, but these remain disputed. In 1572, a new star appeared in the constellation Cassiopeia, bright enough to be visible in daylight. The Danish astronomer Tycho Brahe made careful observations of this object and published his findings in his work De Nova Stella, literally concerning the new star. Tycho's observations proved that the object was far beyond the moon, contradicting the Aristotelian view that the heavens were unchanging and perfect. This discovery was a crucial step toward the scientific revolution. Just 32 years later, in 1604, another supernova appeared, this time in the constellation Ophiuchus. Johannes Kepler, then imperial mathematician to Emperor Rudolf II, observed this event extensively. Kepler's supernova was the last supernova visible to the naked eye in our galaxy. Yes, you read that correctly. It has been over 400 years since a supernova has been visible in the Milky Way. Statistically, our galaxy should produce about 1 to 3 supernova per century, so we're somewhat overdue. When the next one happens, it will be a scientific bonanza. Modern telescopes across the electromagnetic spectrum will capture data of unprecedented detail, and, if we're lucky, neutrino detectors will catch the flood of particles that precedes the visible light by hours or even days. On February 23, 1987, astronomers made a thrilling discovery. A supernova had appeared in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way located about 168,000 light-years from Earth. It was the first supernova since the invention of the telescope to be visible to the naked eye, and it transformed our understanding of these cosmic explosions. SN 1987A was a Type II supernova, the core collapse death of a blue supergiant star called Sangelock -69202. This was somewhat surprising because astronomers had expected red supergiants to be the typical progenitors of Type II supernova. The blue supergiant progenitor forced theorists to revise their models. Most exciting of all, SN 1987A was detected in neutrinos. About 3 hours before the visible light arrived, neutrino detectors in Japan, the United States, and Russia recorded a burst of about 25 neutrinos Orbea, a trace-second interval. This was the first detection of neutrinos from an astronomical source other than the Sun, and provided direct confirmation of the core collapse mechanism. The timing showed that the neutrinos were released when the core collapsed, before the shockwave had time to break through the star's surface. In the decades since the explosion, astronomers have continued to monitor SN 1987 AS remnant. The Hubble Space Telescope has captured stunning images of the expanding debris, interacting with a ring of material that the progenitor star had shed earlier in its life. This ring lit up as the supernova shockwave crashed into it, creating a spectacular cosmic necklace that continues to evolve. One mystery remains. What compact object lies at the center of SN 1987A? Theoretically, either a neutron star or a black hole should have formed when the core collapsed. For years, the center of the remnant was too obscured by dust to observe directly. In 2019, observations with the Atacama Large Millimeter Array finally detected a warm blob at the center, consistent with a neutron star heating the surrounding dust. But definitive confirmation is still awaited. We talked about core collapse in Part 1, but let's slow down and examine what happens in those critical first moments. Because in the world of supernova, a lot can happen in a very short time. The final stage of silicon burning in a massive star lasts only about 1 day. During this frantic period, silicon fuses into iron at the star's core, while the outer layers remain blissfully unaware of the approaching catastrophe. The star looks essentially normal from the outside. If you were observing it from a safe distance, you'd have no idea it was about to explode. Then the iron core reaches the Chandrasekhar limit. Electron degeneracy pressure fails, and in less than 1 second, roughly 0.1 to 0.5 seconds, depending on the star's mass, the core collapses from a diameter of about 6,000 kilometers to just 20 kilometers. That's like compressing the entire Earth down to the size of Manhattan in half a second. During this collapse, several extraordinary things happen simultaneously. First, the electrons in the core are crushed into protons, creating neutrons through a process called electron capture or inverse beta decay. Each such reaction releases a neutrino. The flood of neutrinos is so intense that more energy is carried away by these ghost particles in a few seconds than the sun will radiate in its entire 10 billion year lifetime. The neutrinos stream out of the collapsing core at nearly the speed of light. They pass through the outer layers of the star as if they weren't there, because neutrinos interact so weakly with matter. Within about 10 seconds of core collapse, approximately 10 to the power of 58 neutrinos have been released, carrying away about 10 to the power of 46 joules of energy. This is the single largest energy release of any known astrophysical event. Meanwhile, the inner core has reached nuclear density and bounced. The bounce sends a shockwave outward at tens of thousands of kilometers per second. But here's the problem. The shockwave immediately starts running into infalling material from the outer core. It's like trying to run up a down escalator that's moving faster than you can climb. The shockwave stalls, typically at a radius of about 100 to 200 kilometers from the center. For the supernova to actually explode, something has to revive this stalled shock. This is where the neutrinos come back into the picture, although neutrinos interact very weakly with matter. When you have 10 to the power of 58 of them streaming through a dense region, even a tiny fraction of them can deposit significant energy. About 1% of the neutrino energy is absorbed in the region behind the shock, and this is just enough to push the shock wave over the threshold. The exact mechanism of shock revival remains one of the most active areas of supernova research. Computer simulations show that the process is highly three-dimensional and chaotic. Convection, turbulence, and instabilities all play crucial roles. Some simulations show successful explosions, others show failed explosions, where the entire star collapses into a black hole. The difference often comes down to details of the progenitor star's structure and the neutrino interactions. Once the shock is revived, it takes several hours to traverse the rest of the star. The star's outer layers, still blissfully unaware of the chaos below, finally receive the message when the shockwave breaks through the surface. This is the moment of shock breakout, when the supernova first becomes visible to the outside universe. A flash of ultraviolet and X-ray radiation announces the star's death to anyone watching. From the perspective of the dying star, the sequence goes like this. 1 day of final silicon burning, half a second of core collapse, 10 seconds of neutrino emission, minutes to hours of shock propagation, and then the explosive ejection of the outer layers at speeds up to 30,000 kilometers per second. The entire process, from the last moments of stability to the visible explosion, takes less than a day. After millions of years of steady burning, the star dies in an afternoon. Let's take a closer look at what remains after a core collapse supernova, the neutron star. This is one of the most extreme objects in the universe, a place where matter exists in states that we can barely comprehend, let alone recreate in laboratories on Earth. A typical neutron star has a mass of about 1.4 to 2 solar masses, compressed into a sphere roughly 20 kilometers in diameter. To put this in perspective, if you could somehow scoop out a teaspoon of neutron star material and bring it to Earth, it would weigh approximately 6 billion tons. That's roughly the weight of every car, truck, and vehicle on the planet, concentrated in a volume smaller than a sugar cube. The surface gravity of a neutron star is about 200 billion times stronger than Earth's gravity. If you dropped an object from a height of 1 meter above a neutron star's surface, it would hit the ground traveling at about 2 million meters per second, roughly 0.7% of the speed of light. The escape velocity from a neutron star is about 100,000 kilometers per second, or 1/3 the speed of light. The structure of a neutron star is layered, like a bizarre cosmic onion. The outermost layer is an atmosphere, just a few centimeters thick, composed of hydrogen, helium, and carbon. Beneath this lies a solid crust about 1 kilometer thick, made of atomic nuclei arranged in a crystalline lattice, similar to the structure of metals on Earth, but under unimaginably more extreme conditions. As you descend through the crust, the nuclei become increasingly neutron-rich. The pressure forces electrons to combine with protons, converting them to neutrons. By the time you reach the bottom of the crust, the nuclei have become so neutron-rich that they start to merge together, forming what physicists call nuclear pasta. Yes, that's the actual scientific term. Nuclear pasta refers to exotic shapes that nuclear matter takes under these extreme conditions. Depending on the density, the matter can form structures resembling spaghetti, lasagna, gnocchi, or other pasta shapes. These configurations arise because nuclear forces compete with the Coulomb repulsion between protons in complex ways. Nuclear pasta is thought to be the strongest material in the universe, about 10 billion times stronger than steel. Below the crust lies the outer core, a sea of superfluid neutrons mixed with a smaller number of superconducting protons and normal electrons. Superfluid means the neutrons can flow without any friction or viscosity. Superconducting means the protons can carry electrical current without any resistance. These quantum mechanical properties, which on Earth only occur at temperatures near absolute zero, exist naturally inside neutron stars at temperatures of hundreds of millions of degrees. The inner core remains mysterious. At densities exceeding that of an atomic nucleus, we simply don't know what happens to matter. Some theories suggest the presence of exotic particles like hyperons, which contain strange quarks. Others propose that at sufficient densities, the quarks themselves become deconfined, forming a quark-gluon plasma. Some models even predict the existence of strange quark matter, a hypothetical state that might be more stable than ordinary nuclear matter. Neutron stars also have incredibly powerful magnetic fields. A typical neutron star's magnetic field is about 1 trillion times stronger than Earth's. But some neutron stars, called magnetars, have fields 1,000 times stronger still, reaching 10 to the power of 15 Gauss. For comparison, the strongest continuous magnetic field ever produced in a laboratory is about 450,000 Gauss. Magnetar fields are about 1 billion times stronger than that. These extreme magnetic fields can cause starquakes on the neutron star's surface, sudden adjustments in the crust that release enormous amounts of energy. In December 2004, a magnetar called SGR 1806-220 experienced a giant flare that for a fraction of a second released more energy than our Sun produces in 250,000 years. The burst was detected from 50,000 light-years away and actually affected Earth's ionosphere, despite the enormous distance. Neutron stars are natural laboratories for physics at extremes that we cannot reproduce on Earth. By studying them, we learn about the behavior of matter at nuclear densities, the properties of superfluids and superconductors, the nature of gravity in strong field regimes, and the physics of magnetic fields beyond anything achievable in terrestrial experiments. Every new observation teaches us something about the fundamental nature of matter and energy. If you thought supernova were extreme, wait until you meet their bigger, angrier cousins. Hypernovae are a class of exceptionally energetic stellar explosions that release roughly 10 times more energy than ordinary supernova. And associated with some of these events are gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. Gamma-ray bursts, or GRBs, were first detected in the late 1960s by American military satellites designed to monitor for Soviet nuclear tests in space. The satellites picked up brief flashes of gamma radiation coming from random directions in the sky, clearly not from Earth and clearly not from nuclear weapons. For decades, these mysterious flashes puzzled astronomers. Their origin was one of the biggest unsolved problems in astrophysics. We now know that gamma-ray bursts come in 2 main types: short-duration GRBs, lasting less than about 2 seconds, are caused by the merger of 2 neutron stars, or a neutron star and a black hole. Long-duration GRBs, lasting from a few seconds to several minutes, are associated with the deaths of extremely massive stars. the hypernovae we mentioned. The mechanism behind a long-duration gamma-ray burst goes something like this. A very massive star, at least 25 to 40 solar masses, reaches the end of its life. Unlike a normal core collapse supernova, where a neutron star forms and a shockwave ejects the outer layers, in a hypernova, the core collapses directly into a black hole. As the black hole forms, it begins consuming the infalling stellar material. But not all the material can fall in at once. An accretion disk forms around the black hole. The physics of accretion disks around black holes is complex, but one key feature is that they can launch powerful jets of material along the rotation axis. In a hypernova, these jets punch through the star's outer layers at nearly the speed of light. If one of these jets happens to point toward Earth, we observe a gamma-ray burst. The energy output is staggering. A typical long-duration gamma-ray burst releases about 10 to the power of 44 joules of energy in gamma rays alone, comparable to the total energy of a supernova. But this energy is concentrated into narrow jets covering perhaps 1% of the sky. If the energy were emitted equally in all directions, the apparent energy output would be 100 times higher, making gamma-ray bursts briefly brighter than the entire observable universe. In 2008, a gamma-ray burst, designated GRB080319b, was so bright that it was briefly visible to the naked eye from Earth, despite occurring 7.5 billion light-years away. For about 30 seconds, if you had known exactly where to look, you could have seen light from halfway across the observable universe without any optical aid. The event released more energy in those 30 seconds than our Sun will produce in its entire 10 billion-year lifetime. The connection between hypernovae and gamma-ray bursts was confirmed in 1998, when astronomers detected a supernova SN 1998 BW at the same location as a gamma-ray burst, GRB 980,425. Since then, several other associations have been made, firmly linking at least some long-duration GRBs to the deaths of massive stars. Short-duration gamma-ray bursts have a different origin. In 2017, the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars, an event designated GW170817. About 1.7 seconds after the gravitational wave signal. The Fermi satellite detected a short gamma-ray burst from the same location. This was the first direct confirmation that neutron star mergers produce short GRBs. The GW170817 event was a watershed moment in astronomy. For the first time, the same astrophysical event was observed in both gravitational waves and electromagnetic radiation. Telescopes across the globe and in space turned to observe the aftermath, detecting light from radio waves through gamma rays. The observations confirmed that neutron star mergers are major sites of our process nucleosynthesis, creating heavy elements like gold and platinum. Astronomers estimated that the GW170817 merger produced several Earth masses of gold and platinum, along with significant quantities of other heavy elements. Every gold ring, every piece of platinum jewelry, contains atoms that were forged in events like this, in the violent collision of city-sized balls of nuclear matter. billions of years ago and billions of light years away. How do astronomers actually find supernova? After all, the universe is unimaginably vast, and even though supernovae are bright, they're also rare. In a galaxy like the Milky Way, only 1 to 3 supernovae occur per century on average. To catch them, we need to be watching constantly. The traditional method is simply to photograph galaxies night after night and look for new points of light. Before digital technology, astronomers would compare photographic plates taken on different nights, painstakingly searching for stars that weren't there before. Fritz Zwicky, one of the pioneers of supernova research, discovered over 120 supernovae this way during his career at Caltech. Today, automated surveys have revolutionized supernova detection. Robotic telescopes scan the sky every night, taking digital images of thousands of galaxies. Sophisticated software compares each new image to reference images taken previously, automatically flagging any new sources that appear. Human astronomers then examine the candidates and confirm which ones are genuine supernovae. The Zwicky Transient Facility, named after the legendary astronomer, operates a robotic telescope at Palomar Observatory that can scan the entire visible northern sky every 2 nights. It discovers several supernovae per night on average. The upcoming Vera C. Rubin Observatory, scheduled to begin full operations in Chile in 2025, will take this to another level, scanning the entire visible southern sky every few nights with unprecedented depth and discovering millions of transient objects over its 10-year survey. But visible light is only part of the story. Supernova emit radiation across the entire electromagnetic spectrum, and each wavelength tells us something different about the explosion. X-ray and gamma-ray telescopes in space, like NASA's Chandra X-ray Observatory, the European Space Agency's XMM Newton, and the SWIFT satellite, detect high-energy radiation from supernova. These observations reveal the interactions between the supernova shockwave and surrounding material, as well as any compact object that forms at the center. Radio telescopes observe supernova at the longest wavelengths. Radio emission is produced when charged particles are accelerated in the supernova's magnetic field. By monitoring radio emission over time, astronomers can track how the supernova shockwave expands and interacts with the circumstellar environment. Infrared observations from both ground-based telescopes and space missions, like the James Webb Space Telescope, can peer through dust that blocks visible light. Many supernovae occur in dusty regions where star formation is active, so infrared observations are crucial for getting a complete census of stellar explosions. Perhaps the most exciting frontier in supernova detection is neutrino astronomy. We've already discussed how SN 1987A was detected in neutrinos. Modern neutrino detectors, like Super Cameo Condi in Japan, IceCube at the South Pole, and the planned Hyper Cameo Condi, are far more sensitive than the detectors that caught SN 1987A. A supernova in our galaxy would produce thousands to tens of thousands of detected neutrinos, providing unprecedented insight into the core collapse process. There's even a global network called SNOOS, the Supernova Early Warning System, that links neutrino detectors around the world. because neutrinos escape the collapsing core hours before the visible light emerges. A neutrino detection could provide advance warning of an imminent supernova. SNEWS would automatically alert astronomers worldwide, giving them time to point their telescopes at the right location before the light arrives. Gravitational wave detectors add yet another channel for supernova observation. While core collapse supernova are not expected to produce gravitational waves as strong as those from binary black hole or neutron star mergers, an asymmetric collapse could produce detectable signals. A future galactic supernova might be observed simultaneously in neutrinos, gravitational waves, and electromagnetic radiation from radio to gamma rays, ushering in a new era of multi-messenger astronomy. Now we come to the question that everyone secretly wants answered. What would happen if a supernova exploded close to Earth? Could it wipe out all life? Should we be worried about Betelgeuse, the famous red supergiant that could explode any century now? Let's start with the good news. Space is really, really big, and supernovae are really, really rare. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. The nearest star that could potentially go supernova, Ik Pegasi, b. a white dwarf in a binary system that might eventually become a type Ia supernova, is about 150 light-years away. Betelgeuse, which will definitely explode eventually as a type 2 supernova, is about 650 light-years away. The effects of a supernova on Earth depend critically on the distance. Astronomers typically consider 3 zones of danger. Within about 25 to 50 light-years, a supernova would be catastrophic. The initial flash of ultraviolet and X-ray radiation would arrive at the speed of light, potentially stripping away a significant portion of Earth's ozone layer. Without the ozone layer, harmful ultraviolet radiation from our own Sun would reach the surface, causing widespread damage to ecosystems, particularly affecting photosynthetic organisms that form the base of food chains. Cosmic rays, high-energy particles accelerated by the supernova's shockwave, would arrive years to decades after the initial explosion, depending on how the particles propagate through interstellar magnetic fields. These cosmic rays could further damage the ozone layer and increase radiation exposure at Earth's surface, potentially triggering mass extinctions. Some scientists have proposed that past mass extinctions on Earth were caused by nearby supernova. The late Ordovician extinction, about 445 million years ago, wiped out roughly 85% of marine species. Some researchers have suggested that a gamma-ray burst or supernova could have been responsible, though this remains speculative. More recently, deposits of iron-60, a radioactive isotope produced in supernova, have been found in deep-sea sediments dating to about 2.6 million years ago and 6 million years ago, suggesting that supernova exploded within a few hundred light-years of Earth at those times. Between about 50 and 300 light-years, a supernova would still be dangerous, but probably not extinction level. The ozone layer would be damaged, but might recover within years to decades. There would likely be increased cancer rates and ecological stress, but life would probably survive. Beyond about 300 light-years, a supernova would be a spectacular light show but pose little direct threat. The radiation would be significantly attenuated by distance. The ozone layer might experience minor, temporary depletion, but the effects would be minor. So what about Betelgeuse? At 650 light-years away, it poses no danger to Earth whatsoever. When it explodes, it will be one of the most spectacular astronomical events in recorded history. It will become as bright as the full moon, visible in daylight, and might even cast shadows at night. It will remain visible for weeks to months before fading. But it won't hurt us. The distance is simply too great. The chance of a supernova occurring within the danger zone during any given human lifetime is extremely small. Based on the rate of supernova in galaxies like the Milky Way and the distribution of stars in our galactic neighborhood, the probability of a dangerous supernova in the next million years is less than 1%. We face far more immediate existential risks from climate change, asteroid impacts, and our own technological development than from supernova. However, over geological timescales, supernova do affect Earth's environment. On average, a supernova probably explodes within 30 light-years of Earth, about once every few 100 million years. These events may have shaped the evolution of life on our planet in ways we're only beginning to understand. We've already mentioned that Type Ia supernova were used to discover the accelerating expansion of the universe. But this discovery deserves a closer look because it fundamentally changed our understanding of cosmology. Since the 1920s, astronomers have known that the universe is expanding. Edwin Hubble famously showed that distant galaxies are moving away from us, with more distant galaxies moving away faster. This relationship, known as Hubble's law, implies that the universe began in a hot, dense state, the Big Bang, and has been expanding ever since. For decades, cosmologists assumed that this expansion must be slowing down. After all, gravity is attractive. The matter in the universe should be pulling on itself, decelerating the expansion over time. The big question was whether the expansion would slow down enough to eventually stop and reverse, leading to a big crunch, or whether it would continue forever, with galaxies drifting apart into cold, empty darkness. To answer this question, astronomers needed to measure how the expansion rate has changed over time. This required observing objects at known distances across cosmic history. Type Ia supernova were perfect for this purpose because of their consistent peak brightness. In the 1990s, two independent teams set out to measure the cosmic expansion history using Type Ia supernova. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the Heisey Supernova Search Team, led by Brian Schmidt at the Mount Stromlo Observatory, with Adam Rees playing a key role in the analysis. Both observed distant supernova and measured their brightness and redshift. The results shocked everyone. The distant supernova were fainter than expected. This meant they were farther away than a decelerating universe would predict. The only explanation was that the expansion of the universe is not slowing down. It's speeding up. This acceleration requires something to push the universe apart, counteracting the attractive force of gravity. Cosmologists call this dark energy, though we have no idea what it actually is. Dark energy makes up about 68% of the total energy content of the universe. Yet its nature remains one of the deepest mysteries in physics. The discovery earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics. It was all thanks to careful observations of exploding white dwarfs across the cosmos. Type Ia supernova. These thermonuclear detonations of stellar corpses turned out to be the key that unlocked one of the most profound cosmological discoveries of the 20th century. Today, astronomers continue to use supernova to refine our understanding of dark energy and the cosmic expansion history. The Dark Energy Survey, the Pantheon Plus analysis, and upcoming projects like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory will observe hundreds of thousands of Type Ia supernova, mapping the expansion of the universe with unprecedented precision. Here as a fact that might surprise you. No supernova has been visible in our galaxy since 1604, over 400 years ago. That was Kepler's supernova, observed before the invention of the telescope. The Milky Way should produce about 1 to 3 supernova per century. So, statistically, we're overdue. Of course, statistics don't guarantee anything. Supernova are random events, and the average rate includes considerable variance. Also, many supernova in our galaxy are obscured by the dust and gas that fills the galactic plane. We might have missed some supernova that occurred on the far side of the galaxy, hidden from our view. Still, the next galactic supernova will come eventually. It could happen tomorrow. It could happen in 1,000 years. But when it does, it will be the astronomical event of a lifetime. Which stars are most likely to go next? Betelgeuse gets all the attention, and for good reason. It's a red supergiant that has clearly reached the final stages of its life. In late 2019 and early 2020, Betelgeuse underwent a dramatic dimming event that briefly made headlines, with some people wondering if it was about to explode. It wasn't. The dimming was caused by a combination of stellar pulsations and a cloud of dust ejected by the star. Betelgeuse returned to normal brightness and will probably continue for at least another 100,000 years before the end. Other candidates include Eta Carini, a massive and unstable star about 7,500 light-years away, that has already produced major outbursts and could explode as a supernova or even a hyperstar. There's also Spica, a blue giant that is the brightest star in Virgo, and Antares, the red supergiant heart of Scorpius. Any of these could go next, or it could be a star we're not even watching closely. If a supernova occurred in our galaxy today, here's what we would experience. First, the neutrino detectors around the world would light up. Super Kamiokande in Japan, Ice Cube at the South Pole, and others would detect thousands of neutrinos within a span of about 10 seconds. SNEWS, the Supernova Early Warning System, would immediately send alerts to astronomers worldwide. Hours later, the light would arrive, depending on the supernova's location and whether it was obscured by dust. It might appear as a new star in the sky, potentially bright enough to see in daylight. Amateur and professional astronomers alike would rush to observe it. Within days, it would be the most studied object in astronomical history. The scientific payoff would be enormous. For the first time, we would observe a supernova with modern multi-messenger techniques, combining neutrino data, gravitational wave observations, and electromagnetic observations across the entire spectrum. We would learn more about core collapse physics in weeks than we have in decades of studying distant supernova. For the general public, a galactic supernova would be a shared experience, unlike anything in living memory. People around the world would step outside to see a new star blazing in the sky, a reminder that the universe is dynamic, violent, and awe-inspiring. It would spark conversations about astronomy, physics, and our place in the cosmos. It might even inspire a new generation of scientists. I hope to see it in my lifetime. I hope you do too. Let's step back and consider the big picture. Why should you care about supernova? What do these distant explosions have to do with your daily life? The answer is everything. Without supernova, you wouldn't exist. The elements that make up your body, the iron in your blood, the calcium in your bones, the oxygen you're breathing right now, were all created in stars and dispersed by supernova explosions. The early universe contained only hydrogen, helium, and traces of lithium. Everything else had to be made, atom by atom, through stellar nucleosynthesis. Supernova are the delivery mechanism that scatters these newly forged elements across the cosmos, seeding the next generation of stars, planets, and eventually people. Without supernova, our solar system wouldn't exist in its current form. The shockwave from a nearby supernova may have triggered the collapse of the gas cloud that eventually became our Sun and its planets. Radioactive isotopes found in meteorites suggest that a supernova exploded in our cosmic neighborhood shortly before the solar system formed, roughly 4.6 billion years ago. We are, in a very real sense, children of a supernova. Without supernova, we wouldn't understand the universe. Type Ia supernova revealed that the cosmic expansion is accelerating, one of the most important discoveries in modern cosmology. Studying supernova teaches us about nuclear physics, particle physics, general relativity, and the behavior of matter under extreme conditions. They are cosmic laboratories that test our theories in ways we cannot replicate on Earth. But beyond the practical reasons, supernova matter because they connect us to something larger than ourselves. When you look up at the night sky, you're seeing light that has traveled for years, centuries, or millennia to reach your eyes. Some of those photons began their journey before human civilization existed. And somewhere out there right now, stars are dying in spectacular explosions that won't be visible from Earth for hundreds or thousands of years. Supernova remind us that the universe is not static. It's dynamic, evolving, and endlessly creative. Stars are born, they live, they die, and in their deaths, they give rise to new generations of stars, new planets, new possibilities. This cosmic cycle has been going on for nearly 14 billion years, and it will continue long after humanity is gone. There's a strange comfort in that. We are brief visitors on a small planet orbiting an ordinary star in a typical galaxy among billions. But we are made of the same stuff as the stars. We are the universe becoming aware of itself, looking back at the cosmic processes that created us and asking how and why. That's what supernova mean to me. They're not just explosions. They're creation myths written in fire and light. We've traveled a long way together, from the birth of stars in cold nebulae to their spectacular deaths in supernova explosions. From the iron catastrophe that triggers core collapse to the exotic physics inside neutron stars. From historical supernova witnessed by ancient astronomers to the cutting-edge techniques we use to detect them today. From the dangers of a nearby supernova to the cosmic insights provided by distant Type Ia explosions. Supernova are where astronomy, physics, chemistry, and even biology intersect. They are cosmic forges that create the elements of life. They are laboratories that test our theories under extreme conditions. They are standard candles that measure the expansion of the universe. They are time capsules that reveal the history of the cosmos, and they are beautiful. Not despite their violence, but because of it. There's something deeply moving about a star that burns for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, all the way up to iron, before finally, inevitably, collapsing and exploding in a blaze of glory. It's a story of transformation, of death becoming birth, of endings becoming beginnings. The next time you step outside on a clear night, look up. Every star you see is a nuclear furnace, burning fuel that will eventually run out. Most will die quietly, fading into white dwarfs and slowly cooling over trillions of years. But some will go out with a bang. Somewhere in the sky, perhaps visible to your naked eye, there's a star that will one day explode as a supernova. Maybe Betelgeuse, the red giant on Orion's shoulder. Maybe Eta Carini, lurking in the southern skies. Maybe a star we haven't identified yet, but eventually one of them will reach the end. The iron will accumulate. The core will collapse. The neutrinos will stream out at nearly the speed of light. And hours later, a new light will appear in the sky, bright enough to see in daylight. A cosmic beacon announcing that another star has completed its journey. I hope you're there to see it. I hope we all are. Thank you for joining me on this journey through the explosive cosmos. I hope you've learned something new, felt something profound, and come away with a deeper appreciation for the violent beauty of the universe. If you enjoyed this, please share it with someone who might appreciate it too. Leave a comment telling me your favorite part or what you'd like me to cover next. Your engagement is what keeps this community alive. Until next time, stay curious, keep looking up, and remember, you are made of stars, delivered to this moment by explosions that happened billions of years ago, on the other side of the galaxy. That's not metaphor. That's astronomy. Clear skies, everyone. I'll see you next time.